Our first stop on the rock cycle is sedimentary rocks. This rock type is the product of eroded rocks and minerals that have been buried, compacted, and cemented together to form a new rock. To better understand sedimentary rock, let's visit Jellybean Mountain. Since all rocks and minerals have to come from a parent source, this will act as our parent rock. Now, as the mountain is weathered and exposed to the elements, such as rain or snow and ice, the rocks and minerals are weathered and eroded. Now, as those minerals break off, they are transported with gravity and deposited farther down the hill. Over a geologic time, more and more weathering and erosion will occur, causing continued sediment deposition and buildup. As this occurs, the earlier deposited sediment will be buried and undergo pressure and cementation. This process binds the individual sediments together to produce a new sedimentary rock. Our next part of the rock cycle is metamorphic rock. If sedimentary rock continues to be buried deeper and deeper within the earth, it will be exposed to increased temperature and pressure. To simulate heat within the earth, we're going to put our sedimentary jellybean rock into the oven. And to simulate pressure within the earth, we're going to put a heavy cast iron pot on top. With these forces acting upon the rock, such as heat and pressure, the previous sedimentary rock structure will begin to realign and produce a new rock. Although the rock has changed, it is possible to see old remnants of the structure of the sedimentary rock within the newly formed metamorphic rock.
Our last stop in the rock cycle is igneous rock. When rocks continue to get heated deep within the earth, they eventually melt and form magma. One way magma becomes igneous rock is by traveling upwards through volcanoes to reach the surface. Then magma becomes lava and then cools, creating an extrusive igneous rock. To demonstrate, we are going to take our metamorphic jellybean rock and melt it in a pot of boiling water. Then it's time to cool it down. Now that it's cooled down, we can see how our igneous rock has a different and uniform appearance compared to our sedimentary and metamorphic jellybean rocks.
For our sedimentary rock comparison, we found that our jellybean beautifully resembled a sedimentary conglomerate. Our sedimentary jellybean has visually recognizable large fragments of lithified gravel. These large fragments were exposed to enough weathering to erode them and round the individual fragments, which resembles the shape of the jellybeans. Our metamorphic rock comparison, we agreed, resembled a sample of red quartzite. Although usually a result of metamorphosed sandstone, we found that both the color and texture to resemble quartzite. Our jellybean rock, although exposed to pressure, did not see much realignment in its structure perpendicular to the direction of pressure applied. Our similarity here is that both rocks are non-foliated. For our igneous rock comparison, we chose rhyolite. This rock is classified as a felsic volcanic rock, typically the result of extrusive, explosive volcanic eruptions. Our similarities between our jellybean rock and this rock are twofold. The similarities between textures are a result of the time it took for our jellybean to cool. In our igneous jellybean product, we can also observe large, still intact fragments of jellybeans. For our example, we found these to be similar to the phenocrysts of rhyolite, which showed a slow enough period of cooling for larger crystals to form before the explosive eruption.